do I expect it to work? Yeah, now it's working. Okay. All right. So POD is a linear approximation. So let me go back to what I said last time, and don't worry, I'm not going to repeat everything exactly as was, but I just want to give you a bit of a refresher because it's been a bit of time now. So what we started talking about is that we typically start with a problem where we have a model. This is what we spend all this time figuring out how to deal with. So we have a model, and this model has, let's call it, to be a bit vague, a huge number of components. All right, so it could be a large number of unknowns. For example, if you solve a large fluid dynamics problems, or it could be a large number of parameters or features. So parameters would be, for instance, if you remember, we talked about forest fires where we had a model including Arrhenius' law, which is the amount of energy that's being consumed and how much heat is being generated by that. So these include parameters like heat diffusion, heat conduction, volumetric mass, density, stiffness, bulk modulus, whatever, and so on, and so on, and so forth. Then on top of that, you have uncertainties, meaning that these parameters that we talked about, you have the PDE, they have all these coefficients. It could be, let's say, something like that. And in this B, you have a lot of parameters hidden. That could be a sum of some things on beta I times some sort of function of u. And these beta i's, and that's the simplest way that you can write a function of u, I mean, a linear combination. That stuff is also a parameter that comes from somewhere. This function f can also be parameterized. So at the end of the day, you have lots of parameters everywhere. So you have these bi's, you have these alpha, those are material parameters, for example, but you don't know what they are. And last time we talked about that as well. So that means that if you want to be able to understand anything about this problem, you're not going to be able to do a single run. So the idea is that you cannot understand the problem by doing one deterministic simulation. That doesn't make any sense because the model has uncertainties and parameters that you cannot measure exactly. So doing a single run is not meaningful at all. So then there are different possibilities. Either you're going to test the whole parameter space, or you are going to have some data that's going to help you with the uncertainty quantification, because you are going to then be able to update the model. So if I, let me make a little sketch because I think it's easier. So why do you need even reduced order models? So why? Why is a question that's, in my opinion, always useful to ask. In fact, that's the only question that's useful. So first of all, you may have large systems. So what does that mean, large systems? So of course, large is completely vague, but let's imagine that you have a system where you need to solve a problem ku equals f. I'm just writing this in a completely generic way. This is a matrix, this is a vector, and this is another vector, and you need to solve for u. Let's say that u is your unknown, and let's say that the size of k is something like 1 billion, all right? So it's 1 billion by 1 billion, and you need to solve that thing. And of course, you don't want to solve it for all particular cases because that would be super expensive. If every time you need to invert k, that's going to be super expensive. So for large systems, you may want to have a smaller system which captures the essence, and again, that's not very well defined for now, of the big system. So for example, you have something that has 10 to the power 9 degrees of freedom. So that means that you have 10 to the power 9 unknowns. And you would like to get down to very few, let's say 5 unknowns. And that's going to be what we talk about today. That's one way to think about that. And why is that even useful? Well, because the second reason why you need to solve many of these problems is because you have parametric systems, and they are usually both large and parametric at the same time. If you take weather forecasting, you have billions of degrees of freedom, and you have to essentially solve that very frequently in order to update it due and using the data that you get in real time, right? So if you have a parametric system, again, that can be anything where you have some sort of differential operator, as we wrote down. So, you know, I can just write alpha Laplacian u. I'm just writing some completely generic function plus some sort of sum from I equals 1 to n of beta I times some function of u equals 0 plus some boundary condition. So this is a Poisson problem, and that Poisson problem is one of the simplest you can think of. However, now you have what? Well, you have these little guys, you have this alpha here, you have this beta I here, and now not only you have beta I, but you have that n times. So that means that theoretically here you have something like, let's say, n parameters. If n goes to infinity, it's of the order n. So you have now, let's say, approximately n parameters. And all these parameters, they have an impact on the solution, because when you solve the problem, obviously, these beta i's here, this is just a parametric way to write this parameterized Poisson problem. This beta I is going to have an impact, right? Obviously, because this is a part of the problem, it's going to have an impact on the solution. So if you modify beta I, you're going to have a different solution. Now imagine that you have n parameters, and you need to know where your solution might be when these parameters vary. But these parameters can take many values. You can imagine, of course, that there are these parameters defined by probability distributions. So you can imagine that they are described by some sort of, I don't know, distribution like this, for example. So this is the probability of having beta that has a value whatever. So this is beta I, for example. Each of the betas now has a probability distribution associated with it. Now, if you want to solve your problem with all the combinations of those, you don't even need to go through the complexity of having a probability distribution. You can just do a very simple sampling. Let's say that you have even simply one parameter. Let's make it simple. Let's say you have only one. Let's call it beta 1. And now you're going to solve for the solution to your problem. That's going to be u. And then you're going to have to sample the parameter beta I. So let's say that beta is comprised between just 1 and 2, for example. And then now you're going to have some solutions. You need to split the domain between 1 and 2 into subdomains. Let's say 10 subdomains. And then what you're going to do is you're going to compute for each one, you're going to compute a value, and then another, and another, and another, and another, and so on, until you have 10 of those values. And then it's going to give you some solution, u, as a function of beta 1. But now you can imagine that that's not over, because unfortunately, beta 2 also is varying. So now you have beta 2, and now you're going to sample for beta 2. So you're going to take now 10 samples here, and you're going to solve for your solution. But now you cannot solve for beta 1 and beta 2 necessarily independently. So you're going to have a cloud of points. And if you have here 10 subdomains times 10 subdomains, that means 10 times 10 equals 10 to the power 2 calculations. And let's say that each calculation takes 10 to the power 9 degrees of freedoms, so unknowns. Well, you can quickly compute that you're going to need weeks to just do the 100 calculations on a supercomputer. So that's weeks to months on a supercomputer. And maybe it's not even solvable, depending on the type of problem you have. It might be that you cannot even solve that. Okay, so that's not super cool, because you have, 100 calculation and all that, and 10 to the power 9 degrees of freedom. Let's imagine doing that. That's not cool. So what you're going to try to do is say, okay, well, I'm, first of all, not really interested necessarily in everything in this parameter space. So let's go back to the simple case of one parameter that's varying. So we're going to take simply a beta 1 that's varying, and we're going to take u, which is the solution, and we're going to take some just try to see what is happening in that solution. And it could be that something is happening of that nature, right? So where do you think that it's going to be most important to have some computations done, right? So let's try to just imagine. Of course, you don't know the solution in advance. So that graph that I'm drawing here, you don't know. So all these points, there are solutions that you need to compute, each of them. They are not free. They are not coming for free. So this is a 10 to the power 9 degree of freedom problem, right? Each of them. So that means that, this is not cheap. So when you compute that guy, you can imagine this is not something you do lightly. You need to select what you compute in a smart way. So how do you do that? And that's the whole problem of quantifying dependencies or uncertainties, or you can also call that sensitivity. So these are the keywords. Sensitivity, uncertainty. And you want to quantify these guys because what? Well, let's look at this thing here. So here nothing happens, everything is flat. Oh, here something happens a little bit more. So I have another area where things are happening that's a little better. I mean, let's say more exciting. Here it's again becomes very flat. And here it's absolutely horrendous because this thing is going up like crazy. And you can imagine that maybe you would need more points, right? Because if you need to have a good representation of that curve, well, I mean, you can immediately see that in that region that I'm drawing now, you're going to need a lot more points, so a lot more density of these evaluations than you are going to need in this region here, where absolutely nothing happens and it's completely boring because there is almost no variation of the quantity of interest u with respect to the parameter beta 1. So if you take here, 1 point, that's enough. But how do you know that? Well, you actually don't know anything because you do not know how u varies as a function of beta 1. That is a complete unknown. Actually, it's not completely an unknown. And this is something, unfortunately, I am not going to have time to cover, but I'm going to add in the notes, which I haven't added yet. But it's super interesting and very useful. I'm going to talk about it today, but not do it. You can actually do something which is super amazing. You can compute the derivative. Oh, very nice derivative. You can compute the derivative of u with respect to beta 1. Although, and that is equal to the sensitivity of u with respect to beta 1. And here the keywords are adjoints. So adjoint methods. And if you want to look in that direction, please come back and talk to me, and I can direct you to the literature that's going to help you. Because that's super useful. You can compute directly the derivative of u with respect to beta 1. I mean, not directly, but numerically at least. You can compute that, and you can evaluate in which region of the beta 1 space that quantity u depends more or less about beta 1. And although you don't know the exact solution u, which is super cool. Mm. So that's a very, very nice piece of mathematics which you can use. And I think next year I will spend more time on that, because I think it's much more important than certain topics I chose to cover now that I retrospectively think about it. So yeah, I'm sorry I'm not spending more time on this, but this is very useful. And you can now imagine doing that exactly in the same way for all other parametric directions, right? So you can do that for beta 2, beta 3, beta 5, and so on. And now what you have is you have some sampling. So this is what is called sampling. So you have a sampling here, you have sampling here, and that sampling here is very limited because you have only a few points, maybe even one, and here it's very dense because you have a huge variation, so you need more points. So that's super cool, because now you can sample the space and have an idea where you should use more points and where you should use fewer points. And that's very useful because, again, each of these simulations is 10 to the power 9 degrees of freedom, and you don't want to throw that in the garbage. Let's say, for example, you computed here again a 10 to the power 9 problem, here then 10 to the power 9 problem, here 10 to the power 9 problem. Can you imagine 1 week, 2 weeks, 3 weeks, 4 weeks, 5 weeks of time wasted to compute stuff and sending energy into the atmosphere, and you know, global warming and all these hurricanes and storms and so on that you're creating in Indonesia just because you're computing one more solution? I mean, that's not very responsible. So we need to compute things that we actually think are useful, not just press the enter key and hope that somehow it will be useful. And now we have tools to do that. So in case you're working in that area, just you should know that there are tools that allow you to do that. It's not always easy to use. You need to be a little bit clued up, but there are some very nice tools. In particular, I know some of you are working on this formidable piece of code called Phoenix, which is an automatic transformer of an equation into some code. So you essentially write your equation like this, plus let's make it simple, beta f of u equals 0. And then you say, I want to use a test space that looks like Lagrange polynomial. Then I want to use a trial space that looks like some other polynomial. And then I can directly compute u, and I can also compute the adjoints directly by automatic differentiation in a very, very nice way. So that's one possibility. There are many other possibilities like FreeFem, like Firedrake. So there are very many possibilities that you can use. And there are people in the audience now that are much more expert in this than myself. So I can just refer you to them and they know who they are. Okay, so that's that. You can therefore directly, based on that, get, well, in fact, you can get C++ code directly from the equation that you wrote by hand. So the idea of these things, they are called middleware, where you write your equations in your field of interest, let's say physics or whatever, quantum or whatever environmental problem you're solving. You write it exactly as you would write it on paper, like this. And then there is some sort of interpreter that is going to give you code eventually. And that code is going to be parallelized automatically as well, I mean, most of the time. There are, of course, restrictions because this is so general that it has to include other restrictions. You cannot get anything for free. That's a rule of conservation of difficulty. If you win something somewhere, you lose it somewhere else. That's always the case. But what's nice is that it gives you also the adjoints. So it allows you to compute the derivatives of the solution with respect to the parameters that you are interested in. And we did that in my team with quite a number of people. I can, name a few. Jack Hale is the guy who is really behind everything that was ever done in my team, but also Paul Ozeux did a lot of work on uncertainty quantification for brain biomechanics. And after that, Hussein Rappel, actually contemporarily, did a huge amount of work on Bayesian inference for uncertainty quantification of, let's say, a huge variety of problems. And we have a tutorial on Bayesian inference, which you can find directly online. If you type his name and my name, you will find that. And there is obviously Lars Bake's who has also had a large contribution, in particular in collaboration with Hussein, who was our joint PhD student. Paul was a postdoc a long time ago. He's now in Paris working for the financial industry. So what else should be known about this? Adjoint methods. Okay, so now what we see is we have parametric systems. I think I convinced you that we cannot be completely blind and idiotic, that we cannot compute randomly whatever problem for whatever value of the parameter, that we need to know what we're doing because it's very costly. And moreover, these parameters, they all interact with each other. So it's not just, I compute something with beta 1 and then it's going to give me a solution that's independent of whatever is going to happen with beta 2. Everything is linked and the problems are nonlinear. Typically, so it means, of course, in that case, it's not exactly the case because we have a simple linear combination. But let's say that f was a nonlinear function, and inside here you had some other parameters, gamma, for example, then you would have severe nonlinearities in that problem, which would need to be taken care of. So in general, beta 1, 2, 3, n are not independent. So whenever you change beta 1, you have to basically know what's going to happen to beta 2. So all these things are complexifying the whole issue. Right. So now you can imagine that the actual idea is going to be that you're going to have the following. Okay, so let me go back because I don't want to confuse you. So now I just said two things. I said one thing, which is you have large systems, and second thing, you have parametric systems. So that means you need to have an idea what is, and this is now jargon, the subspace, a low-dimensional subspace. This is what we're going to be looking for, a low-dimensional subspace. So what we're going to have is, I'm going to give you directly what I have in the notes because it's sufficiently well done. And it's not perfect by all means, but it's at least some sort of diagram that you can probably digest more easily. Right. So sorry for copy pasting. I know if you're taking notes, it doesn't make it easier because you need to accelerate your note taking. But since I'm putting all of that online, which you can probably now figure out that everything is on YouTube and all the links are now working, which wasn't the case before. So I hope now that you can watch everything again. So effectively what's going on is the following thing, that you have a continuous problem. This is what I just said, but it's in different words. I'd like to repeat things many times. And then that continuous problem, that's the PDE I was talking to you about, this Laplacian plus f with the betas. You discretize that guy and it gives you a solution. I called it, actually u just above here, I called it x because I'm very bad with notations, but bear with me. And here is the so-called actual state. So what does state mean? These are all the simulations that you make. And then you say, well, I'm not so interested in, in everything. I just would like to have a low-dimensional subspace that's going to go through these points, but it's not going to be exactly those points. Doesn't really matter. I just want something that is an approximation. And that approximation can be a simple line. And that's going to be what is called POD, or Principal Component Analysis, PCA, which everybody hears about because this is the favorite method of any data analyst. Why is it the favorite method? Well, because if you're a bit lazy, and someone gives you a cloud of points, what do? Well, you fit a line through it. So that's POD. PCA, more or less, is exactly that, except now that the cloud of points is in dimension r to the power n. And this is large. Now, what you can do, which is new compared to, let's say, 30 years ago, although it was invented mainly, I would say, in the 80s or maybe even 70s, the idea is the digital twin, let's say, paradigm or blah, blah, that you hear everywhere. So the digital twin is what? Well, it is that not only do you have the PDE, which is the thing that you solve, but again, this PDE, you solve it, yes, but you have all these parameters, alpha, beta 1, beta 2, and so on. All these parameters, you assume that you know that stuff, right? That you have a probability distribution that you measured somewhere in a warehouse in the middle of nowhere, in the desert, or maybe, I don't know, in Antarctica, or in a place where the temperature was variable. You have no idea exactly what you measured, but you measured some stuff. And you have now some probability distribution for one, and then another one for the other one, and so on. But these are done once and for all in a, somewhere someone tested some stuff. I know some of you are working on muscles, for example. So you can imagine that you have a piece of actin and myosin that were elongated in a tensile test machine at 22 degrees Celsius by humidity of 80%. At altitude 200 meters above sea level. But now all these environmental conditions, they were taken at the time. You made some measurements at that particular time, and therefore they're only valid at that particular time, at that particular temperature, at that particular pressure, at that particular altitude, and whatever else is varying there. So you're now hoping that you're going to use those parameters and they're going to be, in fact, useful, but that's very much hope that you are exerting here. You're absolutely not sure at all whether that's going to be the case, because maybe your model is going to be used for an organism at 37 degrees without external pressure, or at least only the internal pressure of the body. You're maybe going to be using that for astronauts that are going to be in a space station where the conditions are again different, are being irradiated and so on and all of that. So this is not working very well, right? So this is the standard, typical way that we've been doing things. And this is what I was telling you last time about Paris law, that you do simulations, you do tests in the lab, you break some concrete, you break some steel, you cycle a piece of aluminum using any sort of loading machine under fatigue, and you look at the cracks and you look at the microstructure, you look at all of that, and at the end of the day you have a law that tells you how much the crack grows if you know the energy that you're putting into the system. So that's something that's empirical, or at least semi-empirical. And this works very well. People use it every day in, for mechanical engineering, aerospace engineering, to send rockets in space, to have aircrafts that fly for 20,000 years without failing. I mean, it's absolutely amazing, the level of usefulness of these things. However, everything is set in stone. All these parameters are blocked, and they are whatever they are, and you just know these probability distributions, and that's it. If you want the equivalent in design code, so everybody that's an engineer, or at least knows engineers, well, you will now be able to tell them that whatever they use as design codes comes from probability distributions. So let's say that you are going to design a building. Well, you don't know how much rain you're going to get on that building. You know also not how much snow you're going to get. You don't know the wind load exactly, but you know some distributions of these things. And so when you do the building code, you need to take into account the combination of all these particular loads, and you need to take into account the worst possible case, because you want the ultimate load that the structure will undertake. So you are going to look at the same time, having the maximum snow load, the maximum wind load, and the maximum earthquake load all coming at the same time, which is very unlikely, never happens, but you're going to design your building against this, such that you're sure, more or less, that at least these combinations of events are not going to ruin your building. So, you do that for bridges, you do that for dams, you do that for constructions where you put actual people in them, and so on. Right? So that's what you do. And you have coefficients that look barbaric, like 2.37 root 3, and these things come from statistics. They just come from statistical distributions that you computed, and everything is fine. Okay, so that, again, that is all a priori. Now, we are moving in a world where things are not a priori anymore. We would like to have the ability to take data in real life, so real-time data, and use it directly to update the state of the system. What does that mean? As I said last time, and I want to repeat that because this is highly important, if you have any sort of structure, I'm just going to take something very easy, like an airplane. So an airplane is like this. Bear with me for the huge, amazing design of this Airbus A380 with 2 decks and many windows for 500 passengers. So that little thing is going to be now full of sensors that are now in the wings, let's say, and they are in the fuselage. So this is a fuselage. They have now sensors, and all those sensors are going to constantly send information in terms of what is going on in that structure. So that's the idea, right? You have not only those sensors, but you have other sensors like You know, here you can measure the velocity, you can measure the pressure, you can measure all sorts of things on the wings, you can measure the temperature, you can measure everything. So you can measure a lot of things at least. And based on that, you would like all these sensors to give you an idea of the state variables. So you'd like these sensors to give you something about, okay, now I just measured U or X, you know, depending which notations you use, which is the unknown that I'm interested in. I just made a measurement of that. So I'm not looking for that anymore because I know it, right? So how does that help? Well, it helps a lot because if you solve your problem in an agnostic way about the current environment, you're going to just get one solution or a series of solutions or an average solution or an expected value of the solution if you're doing that statistically. And what does that mean? Well, it means that you have to contend with all the uncertainties, but now the uncertainties are embedded in whatever you measure here. So this U, which is measured, or this X, which is measured, those take into account the uncertainty. They are no longer calculated at temperature in the warehouse, you know, where you actually made the measurement in the first place. I can see that my drawing skills are getting better with time. So if you here have your little loading cell, you know, that would have given you parameters alpha, beta, and so on, which are quite different from the alpha and beta that you have in the sky, because the temperatures and the velocity and the pressure and everything else are completely different. So why would these parameters be the same? So that means that now, if you have your computer model of this wonderful aircraft, which you can imagine is somewhere here. So now you have a computer model of your aircraft with your computer being there and a little nice keyboard and mouse, because we are last century. Then you can imagine that that computer model now is going to be able to be updated by the real model. And these things are going to converse with each other. So that guy up there is going to give me a value of the parameter. It's going to give me maybe some U, maybe some X is going to be the solution. And then I'm going to update my model. So the model now is state 0 is going to become state 1. And with that new model of state 1, I'm going to make a prediction. And that prediction I can actually send back up. And possibly I could now actuate something, whatever here, you know, there may be some actuator or some gear, or I don't know, I really draw very well today. This is really horrendous. So there can be here something going on, actuation. So we're going to call this actuation. So you can really imagine that you have whatever is going on, and you are going to be able to actuate something. You're going to make an action based on this. So for example, the flaps will go up, and you're going to increase the drag, or down, or whatever. So, but you're going to increase the drag, right? Because you realize that if you don't do that, there can be negative effects on the structure. I'm just making things up now, but these are very real, and they are used in practice. They are used at companies like Goodyear in order to optimize the surface of the tires that you are using in your car. Because you know, if you make them in the wrong way, you will have these surface effects that are very deleterious to the stability of the tire on let's say, any sort of surface. So that is what people call all the time digital twin, right? So a digital twin is not what you think it is. So it's not a model that is set in stone like that one that comes from the warehouse where you did your experiments. Okay, so that is not a digital twin. A digital twin is a living model of a living structure or living system. So that's the system, and that thing is living its own life. It is living its own life, and in parallel, this is the model of the system that is living also its own life. But now, every time something happens to the real system, the model system learns about it and can be updated. And you can imagine applications of that in any field, really, that you're interested in looking at. And the success of that obviously relies on what? Well, that prediction that is here, that guy should be fast. Okay, impossible if you need to make a prediction that takes 1 week, because the airplane is already landed and whatever you wanted to do on that airplane is now useless. So if you take another application, which some of you are interested in, surgical simulation, you're trying to help a surgeon make a decision. They are currently performing an incision somewhere, and they want to know if by increasing the pressure, they will or not destroy a capillary, which will create bleeding. Well, if your model takes 1 week to come up with a simulation results, then of course the person on the table will have a hard time surviving. So that's the point. You don't want that. You need to be very fast. You want to be efficient, and you cannot solve the problem of that aircraft on a computer in 1 second, not even less in a millisecond. Same thing for the brain surgery or whatever surgery you're making. You need solutions in, let's say, less than a few seconds. And if you make a full model of the system, you're going to talk about hours to weeks. So you don't want that. So you need to be able to focus the computational expense where it's needed, and you need to accelerate stuff. So I think now that's pretty clear. So now let's look at what you do in POD, because that is the most simple way that you can reduce a system. So proper orthogonal decomposition. Right, so that's a very old method that people came up with as soon as they started thinking about these things. And it's usually done for dynamical systems because you can imagine that you have solutions. And now the idea is very simple. The idea is that if you want to have this model, and I'm going to afterwards show you a very clear example of that. So I'm going to repeat that 5 times today. So I hope that's not going to be too boring for you. But at least I hope that by the end of the lecture, you'll have a good view of what we're talking about. Right. So now, what we're trying to do is we're trying to accelerate the problem. So what does that mean? Well, it means that we are going to be, and this is also jargon, but I want you to understand what that means. So I'm going to use that jargon. This jargon is called this we talk about online. So this is going on online. So online means the aircraft is in the air and you want to make a decision now. The patient is on the table, you want to know what to do now. That is the online simulation. So online simulation, they are fast, but have limited accuracy. So when I say limited, of course, that doesn't mean anything, but it means that they are not the most performant in terms of accuracy, right? But they are in terms of speed. So you have a trade-off. And so what is offline? So offline means aircraft on the ground, you will do offline calculations. So what would you do? If I gave you a simplified aircraft, not offlines, but offline, why do I write like this? Offline. Let's say that I have a very simple aircraft. So the very simple aircraft looks like this. It's extremely simple. And now I'm going to assume that I want to simulate that thing online. So I want to have a model of that is going to run very fast. So I don't want to actually calculate everything. I want to know online what's going to happen. So what do I do? Okay, Online, I don't know what's going to happen. As you realized, online, I don't know what the load is going to be. So let's say that here there is some sort of load coming in, and here there is another load, or the temperature is changing, or a bird is striking the, that can be kind of bad, but sometimes you have these birds that strike the engine, and you need to know that your aircraft is not going to go down because a bird strikes the engine. And there are actual tests made by companies like Rolls-Royce or General Electric, where you send some fake birds that are made of jelly inside a fully functional real engine. So you make an actual test with the real engine. You can look at that on YouTube. It's amazing. Some of my colleagues in Nottingham were working on this at Rolls-Royce when I was in the UK. And this is absolutely amazing to see. You send some virtual sort of jelly inside the rotating engine at full power. And then you see that if there is any explosion, which there will be, you can also do something even weirder, which is to put an explosive charge on one of the blades and look at what happens. And what should happen is that the container of the engine should be able to contain the explosion so that nothing comes out of the engine and starts to puncture the cockpit or the fuselage and kill people, right? So everything, all the explosion should be contained inside so that nothing happens to the passengers. And of course, then there is another issue, which is that the plane should be able to continue flying with only one engine. So that is a different problem. But the first problem here we're interested in is to figure out what is going to happen to this engine if a bird strikes, for example. So this is a load that you don't know, because you don't know if the bird will strike, and you don't know how big the bird will be striking, if it's a small bird or a big bird, if it's going to strike in that direction or this direction, if it's going to come in that way or that way. So you have no clue what's going to happen. So this is the online problem. The online problem is unknown. You don't know what the load is going to be. You don't know the magnitude, you don't know the direction, you don't know anything, the application point, nothing. Okay, and now this is going to have to be solved in, let's say, 10 to the minus 3 seconds. So you need to get a solution of that problem in 10 to the minus 3 seconds, but you don't know what the load will be. So that's the question you're asking. And now, well, let's say that your boss comes to you and tells you, okay, now you have 1 week to prepare for this challenge. The challenge will be you have 10 to the power minus 3 seconds to predict the deformation of that beam. So let's say, for example, if I take a very easy case of that airplane deforming, I mean, I like this example because it's very visual. You can immediately imagine how it looks. You're going to, let's say that the load is super simple. Let's say it's in the middle, but you don't know it yet. Huh? So the beam is going to deform, and it's going to deform like this. And you even know how to compute that. But you have only 10 to the minus 3 seconds, and you don't know what this load is going to be, nor where, not magnitude, application point, nothing. Okay, so now your boss tells you, okay, you have now 1 week to perform pre-computations. And your question is, what pre-computations should you perform in order to minimize the error on that displacement here? That's the question. So in other words, you're going to be allowed to solve that problem, and that is called offline, because you don't need that to be fast, but you need that to be smart. So you need to perform smart calculations, meaning the ones that matter, such that when you are now in the online phase, you're going to want to be fast. So here it's slow but smart, and then you want to be fast and less accurate, obviously. Okay, so then that's the question. Your boss comes to you and tells you, okay, you have now 1 week, please perform the simulations, and then I'm going to tell you, you're going to be able to tell me, if I give you any load, what will be the deformation. Oh, okay. Well, so what you can do is you can say, okay, well, I can apply a load in the middle, for example, or then I can make it move to the right and to the right and to the right and to the right and so on. And so I can, of course, do that. And then for each load, I'm going to record the displacement, right? So I'm going to do that for all the loads that I can manage. And if everything is linear, then it's easy. If it's not, that's what we'll see later. It's not as easy because it's not so simple to just use the same load everywhere and just use superposition. If things are nonlinear, you cannot superimpose anything onto anything. So then what do you exactly do? Well, you can do exactly that. You can do, okay, well, now I'm going to apply a load P1, and then a load P2, and then a load P3, and then a load P4, and then a load P5, and then a load P6, and P7, and P8, and P9, and then I'm going to do what? Well, that's what you do in POD. So in POD, what you do is now, okay, I want to solve all that stuff. Well, I'm going to now compute what is called snapshots. So this is called snapshots. So snapshots is the word is pretty easy to understand. It comes from the idea of a camera, right? So you take a camera and you want to take a snapshot of whatever, and you look at something and you record the deformation. So I will take, let's say, P1, and I will record the deformations. I'm very bad at drawing deformed curves, so maybe, don't even look at this. It's horrible. Okay, so I'm going to take one load. P1 is going to give me one deformation, and I call this one U. I will call it, actually, I will call it X because I call it X in the notes. So it's maybe better to at least have one notation. So that guy here is going to be X, and that's the one online. So this P1 is going to be X leading to X1. This P2 is leading to X2, right? And then you can keep going, and this Pn is going to lead, actually I used M, so let's call it M, is going to lead to Xm. And each of those typically is going to belong, so Xk is in R to the power N, and N is the size of the solution vector. Okay, so what we want is we would like to know what could be a low-dimensional linear subspace such that all the snapshots are well approximated by the vectors in VR. So we're going to look for VR, which is low dimensional. Why? Because then we need to use that online, so we cannot afford to have anything slow. And it's going to be composed of R vectors or R snapshots, which are called snapshots phi1, phi2, phi r. And all we know, and this is included in R to the power n, which means that, so that is going to be the snapshot, right? So that's the reduced space. And that is included. So this is smaller than R to the power n, which is the original size. Understood? So for example, just to make things easy, if I compute in that particular case, I'm going to compute the deformation for P1. I'm going to get one curve. Okay, that's going to be, let's say, X1. Then I'm going to compute it for P2. I'm going to get another curve. That's going to be X2. Then I'm going to compute it for X3. P3, I'm going to get X3. And you get the picture until I get that for all cases. Okay? And maybe sometimes I get some weird things like this, you know, and that's maybe XP. And whoever cares, it just gives me whatever it gives me, and I get whatever I get, right? Okay, so now I have all these solutions, and I put, we will see what we do with that, but we're going to put that in some matrix, and we're going to extract the substance of that matrix to make it as relevant as possible to the exact problem, right? So you noticed that here, I will actually make another one that I will call PM, because this PM, which is here, corresponds to this PM, which is here, which is the maximum number of solutions that I'm storing. Okay, so now I have snapshots. The snapshots are these curves. Okay, so all these guys here are snapshots. Okay, you can really imagine you take a picture of the deformed beam, and that gives you an idea of how it deforms. And now you have a lot of them, and you need to extract something which is much smaller. So now you have a new thing in there, which is R, and R is much smaller than the original size, right? So much smaller than N. All right. So in practice, it's going to be 2, 3, whatever. And now that's it. You essentially are going to say, okay, what is the essence of what I learned from the snapshots? So once again, these guys are snapshots. And the question is, so maybe I should give it this nice little color so that it makes some sense at least. So those snapshots, they are in a space which is whatever of dimension Rn, right? So there are lots of points there. And now I'm going to try to say, okay, what do I do with that? So I define S, which is a snapshot matrix. All right, so I define S. S is a snapshot matrix. What do I do with the snapshot matrix? Well, I say, okay, well, I'm just going to define it, and I'm going to put in that snapshot matrix, I'm going to put everything. So I'm going to put the first, and then the second, until the mth POD mode. Sorry, not POD mode, snapshot. I'm ahead of myself already. And that guy has n rows and m columns. So here we have, so what is the color of M? Okay, I think that's suitable enough. It has M rows. And yeah, I know I should have given it a different color, this N. Maybe I will do it now to have a little bit of logic. So this N I'm going to color differently so that you can see at least a difference in principle, right? And here it's going to have n columns. So n rows, m columns. So that means that that thing is a matrix that is in R to the power n cross m. That is that matrix. And what do you think we're going to do with that matrix? I would bet that you already know. Well, first of all, it's not square, so we cannot compute eigenvalues. But what can we compute? Everybody knows. Thank you very much. We will compute singular values. Nothing breathtaking. So we're going to simply do a singular value decomposition. So SVD, singular value decomposition. So for those of you who don't know what it is akin to an eigenvalue decomposition, but when you have non-square matrices. So everybody learned eigenvalue decomposition, that's for sure. And those of you who didn't learn the general case, well, the general case is exactly the same as the other case, except that the matrices now they have a different shape and different size. It's usually written U sigma V transpose. So that is a typical singular value decomposition. So what are the sizes of these guys? Because that's obviously important. So what are the sizes of those guys? Well, we can immediately see, and now I'm going to struggle with the colors, but big U is n times n. And it has orthonormal columns. Those are the left singular vectors. So it's an orthogonal matrix. And V is the small guy. So V is this guy. And it has M times M. And of course, it is called the right singular vectors. And what is sigma? Well, sigma is obviously n times n, because otherwise there is an issue in whatever I've written here. And that is known as the singular value. So this is a diagonal matrix with the singular values, which are usually called sigma 1, sigma 2, sigma what? Okay, it's n rows, m columns. So that's going to be sigma n, if I'm not mistaken. At least that would make sense to me. All right, so you have n rows, so like that, and m columns like this. Now sigma, actually, I don't even know, because let's just leave it. Okay, so now we have these singular matrices, okay? And we can order them. So normally in eigenvalues, this is called lambda 1, lambda 2, lambda n. Here it's called sigma 1, sigma 2, and so on. And we can order them such that sigma 1 is greater than or equal to sigma 2, which is greater than or equal to sigma 3, which is greater than, to 0. So they're all positive on the diagonal, and that's what gives you the importance. So you can rank them, and what we're going to do afterwards is we're going to look at those guys, and we're going to say, okay, the first one is large, the second is smaller. Okay, so the first one is large, the second is a bit smaller, and then the third one is yet smaller, and smaller, and smaller, and smaller. Okay, and so at the end of the day, you end up with a ranked eigenvalues, and the first ones are the largest, meaning the most important. And the next ones are less important, meaning that energetically, so there is a lot of jargon in relation to mechanics, because energetically, because you probably realize, I'm talking about mechanics not because I did a PhD in theoretical and applied mechanics, but also because this is where all these numerical methods were born. People were trying to build some stuff, usually civil engineering. This is where finite elements were born. They were trying to look at impacts of airplanes on nuclear reactors and try to figure out what's going to happen to them. So these are really the beginnings. Everything came from mechanics. So that's why I always use these analogies. For example, Ku equals F is not necessarily stiffness times displacement equals force, but because you can solve that for any type of problem you're interested in. But usually this is the notation that people use, because K is usually the spring stiffness, U is going to be the displacement of that mass, and F is going to be the force that you apply on that mass in order to displace it. So that's typically the way people talk, but it doesn't mean that it's only applicable to mechanics. obviously, I think I convinced you of that because we talked mainly about other problems than mechanics, but just want to make that clear. So now we say energetically, so this is again some sort of at least physics-based interpretation. That means that the first eigenvalue, or sorry, the first singular value is a value which is going to be more important than the other ones, right? So now what we do is we say, okay, what are we going to use as singular vectors? That is the question. So we take, and you remember now the R is going to come again into the equation, R, which is much smaller, if you remember, let's go back up. Yes, this R is much smaller than N. And this is what this is what governs the size of the snapshots. And we already looked at that here. Yeah. All right. So now we are going to select the first R left singular vectors as snapshots. Right, so we can write it in some way, it doesn't really matter. We can write it phi I equals U, the first column being, row being whatever it is, and the column I equals 1 to R. So that's what we choose. And why is that even cool? Well, what is really cool is that, first of all, you can take VR equals the span, so all the linear combinations of these phi 1, phi r, and that is a reduced space which contains the information you need. And what is cool is that depending where you truncate, so that is, you truncate at R. And what we're going to see in 1 second, that we know in advance what is the error in the projection. So let's first, before talking about the error, talk about what it actually means. We have some sort of optimality here. So for each snapshot, xk, what is that vector that I'm writing? So xk r, yeah, okay, notation is not perfect. It's far from perfect. Let's look at this quantity and tell me what that means. So phi I transpose xk times phi I. So what is that? So I think if you did a bit of linear algebra, you see that this is the projection of xk onto VR. Right? Why? Because VR is made of these basis vectors, phi I, and you're simply computing the sum of the projections of xk on these basis vectors. And what we can show, which I'm not showing, is that, so we can show what can we show? We can show that so VR, which is the POD space, so that's the one already you want to compute offline, right? That's computed offline, minimizes the error. So what error? Well, it minimizes the error sum from k equals 1 to m of the norm of xk minus xkr squared, and this is L2 norm, yeah, it's just L2 norm, which is the Euclidean norm, so sum of the squares. So that stuff is what you minimize. So what does that mean? Well, it means that the snapshots are, the VR is minimizing the projection, the difference between the snapshot xk and its projection on the basis. And what is even cooler is that you can actually show, and this is really, really nice and very useful, you can show that that guy, so that error, let's call it, I don't know what, okay, I won't call it anything, is equal to the sum from I equals R plus 1 to, okay, this is a bit awkward the way I'm writing it, minimum of n and m, sigma I squared. But now let's look at, let's just copy paste what we have here. And bring it back there. And we can maybe even enlarge it a bit. So what it says is that the error that you're looking at is depending, if you truncate at the first mode, then the error has to do with the sum of all the remaining, of the squares of all the remaining singular values. Okay, so sum of sigma I squared from I equals 2 to whatever. Okay, the final one. Okay, what does that mean? Well, it's super nice because it means that you know in advance what error you're making. I mean, and there's nothing cooler in simulations when you know in advance what error you're making, because, well, you can exactly know what's going on, right? And that I think is pretty useful. Okay, so that's for that. Now, if I truncated at the next, okay, so now let's imagine that so I'm going to cheat really a lot, which is very bad, but actually, I don't know if I'm going to be able to cheat that badly. Let's see if that thing lets me. I guess it won't. Oh, it did. Good. So now if I truncate a bit more, a bit further, so if I take 2 eigenvalues, well, then now the error is decreasing, you know, every time this little yellow blob is getting smaller. And if I keep decreasing that, then I'm going to be able to decrease the error further and further until I'm satisfied. And the question obviously is, when am I satisfied? And that is a general question for humankind, but also an interesting question in that particular case, because we are in fact never satisfied, but we need to have a compromise between having too many snapshots which take too long to compute and having too few snapshots which do not capture what you're interested in capturing in the problem. And that's what I'm going to tell you about in the presentation that I show afterwards, which I think makes everything super crystal clear when these methods break down and how you can use these methods in a more general way when they actually don't work out of the box. And I think that's really what should show you immediately the state of the art in the field. I mean, I'm not saying, not even claiming that I'm getting close to the state of the art, but at least logically, you will be, able to do that nicely. Okay. All right. So in the notes, what I do is I give you a worked example, which is in version. Bear with me a second. I find the proper version number of this thing. I don't find it. Give me 1 second. Yeah, version 6. So book version 6. So if you download all the versions one by one, at least you will have you will have the proper page numbers, because it's evolving so quickly that page 198, you have a worked example for just a few snapshots. I think it's 3 by 3 or something in R2. So, you can play with that, compute everything, the correlation matrix and so on. And it's a few pages of derivation, but that's pretty cool. Right. And then it gives you also on page 201, you have the algorithm, which is a very simplified algorithm. It's not even a pseudocode. It's a really very basic thing. Build a snapshot, compute SS transpose, solve the eigenvalue problem, sort the eigenvalues or the or the singular values, define the modes, and then normalize, and then choose R so that your relative energy R is as small as you want it to be. For example, 99%. And that's it, right? Right. So now 2 things I'm going to do. The first is I'm going to tell you a little bit about what is going on when things do not work. And I guess that each of you, being a smart person, having an idea what eigenvalues do, let's call it beyond pod. Well, sometimes it might be, so let's imagine that you have a snapshot solution that looks like this. And now you're trying to fit whatever snapshots matrix to this and find something which makes sense, right? So what you're doing in snapshots, let's say that you have 2 of those, x1, x2, what you would do, well, you would do something like that. So you would take, this is POD. I mean, obviously, that is totally dysfunctional for the problem that I just drew, because everything is totally weird. It's going in all directions. It's looking like, some curve or something. And, that's not at all suitable for a linear approximation. Or if it is, well, it might be that you need a different POD for different cases. So it might be that depending where you are, you need another POD, and then another POD, and so on. And that's not super practical, because you need to recompute it all the time, So that would be what POD would look like. So you don't want that stuff. You would like to have something which is going to allow you to do things more generically, and this is called a manifold. So solution, so manifold. So manifolds come from functional analysis, but now that's not what we're talking about. It's just something curved. So you can just remember that this is curved, and this POD, that is linear. So that's a linear space, it's a plane, it's a hyperspace, it's whatever you want to call it, but it's not curved. And so what you can do now is that even if, because even if the PDE is linear in X, the map from mu to X of mu, if mu is some sort of parameter vector, that is probably nonlinear. right? Geometry, boundary conditions, parameters, and so on that we talked about. And for nonlinear PDE, the solution manifold is even more nonlinear. So if you use POD or PCA, you approximate the manifold only locally, and for strong nonlinearities, you can forget it, and you will need some nonlinear approximation space. Okay? So I'm not saying more about this, but you can imagine that there are several ways that you can deal with that problem. And I'm, of course, not systematic here. I'm not going to be exhaustive. I cannot tell you everything that's going on in the literature, but I'm going to show you now pictorially what happens, not without deriving anything, because there is no point now. But I'm going to show you what you can expect if you start playing with nonlinearities like this, okay? So I think it's clear to you now that if you have a solution which is highly nonlinear and you try to approximate it by a line, that's working very poorly. So now let's just try to make a better drawing so that you can understand better. So let's imagine that we have some solution x1, x2, so we have two only in R2, just to make it simple. And what could we be trying to do now? Okay, so as we said, if we use POD, what's going to happen is we are going to take some sort of local approximation. So what we could say is, okay, well, we could take POD here, and we could take another POD here, and then another POD there, and so on. So it means every time you need to compute the new basis, right? That would be VR1, here VR2, and here VR3. Turns out that works pretty nicely. And you can do what is called domain-based reduced order models. So domain-based POD. And what that is extremely trivial to understand. What you would do is you would do that. So you would have one area here, that would be a first subdomain. Then you would have another area from here to there, and a third area from here to there, let's say. Here you would use VR1, here VR2, and here VR3, because I decided to write from right to left. Why not? And now I'm going to use for each subdomain a different POD basis. And I'm going to show you afterwards an example where you have no choice but to do that, which is a super cool example, which we've been working on with a colleague, Pierre Kerfriden. In fact, if you want to look at the literature, he's one of the best people to look at. You can also look at Patera at MIT, who works on a method called the Lego blocks. And you can, of course, look at Charbel Farhat in Stanford. Pierre Kerfriden is at École des Mines de Paris, and he was in my team for a long time responsible for dealing with all the multi-scale aspects and all the reduced order model aspects. And there are many others. I'm not exhaustive here. I'm sorry for the others that I'm forgetting. This is not intended. It's just the work that I know best. And if you take a look at those people, you will directly see the type of examples that I'm talking about. And with Pierre, we did that for fracture mechanics, and I'm going to show you examples of that afterwards. Okay, so that's one method. The other method would be slightly different, which would be to try to use manifolds. So the idea of using manifolds is exactly as I said before. Instead of approximating using lines now which are straight, you're going to try to approximate using something which is now curved. So those are, and here there is a whole theory behind that. And in my team, the lady that is now at LIST is called Eleni Koronaki, and two PhD students worked on this, and she worked with Brown University as well, with Kivrekidis and so on, the inventors of the method PINS, which is not exactly related, but not so different either. So you can take a look also at Brown. And the Technical University of Athens with Bouvoudis, because they work together. But if you look at her, or even go to talk to her, because she's now in LIST, and she's very approachable and very friendly, and always happy to help. So you could go and talk to her if you want to have more details on that, because I'm not able to do any justice to that method now. Right. Now, what I want to tell you before we move to the rest is what is PCA, just in 2 seconds, and then a little bit on how these neural network style methods relate to what we're talking about now. I'm conscious I've been speaking for 1 hour 34 minutes. If you want to take a quick break because you may be wanting to stretch your legs, I'm going to I'm not going to disconnect, but I'm going to reconnect in so 1 hour 34, maybe in 2 minutes at let's say 3 minutes. At 10:37 I will reconnect, and we can then continue with what we've started. I just want to let you a chance to move around because it's been now already too long. So please stretch your legs, do some burpees and some squats and push-ups, and then we'll come back in 2 or 3 minutes. So just, I have to, do I mute this? No, it's too complicated. Okay, so see you. Okay, so I hope everybody's back. It was a short break, but hopefully good. All right. Now, what is PCA? And again, I'm not covering any part of the details. This is page 203 of version 6. So what I'm talking about there is now PCA is some sort of statistical version of POD. Okay. So what does that exactly mean? Statistical version of POD. So that's what we're going to see very briefly. Now we assume that we have data points, but data points can be generated numerically, as we said before, but they can also be measured. That's the cool thing. So the data points, we call them x1, x2, xm, and those are again in r to the power n, and n again is large. And so the idea of PCA, so PCA is going to find orthonormal directions u1, u2, and so on, ur, again, r is the most, as small as we can make, where the data vary the most, right? So that's a very sort of hand-wavy explanation of what that is. So then what you do is you're going to project on the span of u1, ur, and it's going to give you the best r-dimensional linear approximation in terms of least squares. So what does that mean? It means if you have, again, these data points, x2, these data vectors, rather, x1, x2, so we assume that we have maybe a bunch of points. What PCA does is it's going to draw some sort of, you can imagine this sort of cloud, and it's going to give you two directions, u1, u2, which are orthogonal. I mean, and you can normalize, obviously, by dividing by the norm of u1 and u2. And it's going to give you an idea of what is this data cloud. Okay, so u1 and u2 are the directions of maximum variance. So that's where the data varies more. That's it. Okay, so you can use that for many things. Pratik, who presented in the discretization methods course last week, talked about that for shallow water equations, for example, how to transfer from Navier-Stokes to shallow water, depending on geometry. So you can use that for statistical methods analysis. You can use it for medical analysis, for single cell data sequencing. I mean, you can use it for anything. But again, it's got a linear flavor. So that is the limitation of that PCA. Okay, so now what about neural networks? Because you're all obviously interested in neural networks because everybody talks about them, but also because they are extremely helpful tools. So you can use also neural networks to perform approximations. So I'll give you references later. Well, actually, I can give them now. In my team, Saurabh Deshpande, Jakub Lenkiewicz, So if you look for their papers with me, you will find what they have done on neural networks, but also on graph neural networks, so on convolutional neural networks, to accelerate and create surrogate models. Again, Eleni Koronaki, plus her PhD students and myself, have done a huge amount of work also in that area. So, if you look for their names, you will be able to see whatever we have done. And in there, you have lots of references. I think the papers are pretty good to give you an idea of how to, how to actually do use neural networks for these particular problems. And you can, in fact, use neural networks use them as nonlinear maps to represent manifolds. So now, if you think about a neural network, that's something like a function from R, so the real numbers to the power small r, to the real numbers to the power big N. So that thing is low dimensional. Input, people call it also latent space for some reason, or latent variables. To a space of high dimensions, and that is the output. Okay. So again, same coloring as before. It works pretty much exactly the same way. And now you're assuming that, just assume that the solution X, that is the solution you're interested in, is a function of some parameters, mu, and what you want is to approximate this X of mu by a neural network F, capital F of mu. And that guy is still a member of R to the power N. And this mu is a member of R to the power R. So what does that mean? Well, it means that you're trying to find the parameters that have R in terms of dimensions. So you're trying to find R parameters that are going to give you as much information as N, effectively. So that's all the latent variables or the latent space. And that's very similar to what you can think of what we did in POD, because in POD we ended up with this R somewhere or other. Yeah. Here we ended up with this R, which is the truncation at which we stopped the approximation, right? Remember that. So now it's exactly the same thing. We have a little r, and this little r is the size of that we are willing to deal with. We don't want to deal with the full size of things. We just want to deal with a smaller size. And that's it. So now you can use this F as either a black box, and that then becomes a black box surrogate, again, surrogate, as I told you last time, is something that replaces, substitutes the actual model, but is simpler to evaluate and cheaper. So this is what we need online. So that's the black box surrogate. You can also use it as a building blocks for pins, which are these so-called physically informed neural networks, where you don't only use data now, but you use data constrained by the partial differential equation that you're working on. Right, so that we talk about in the discretization course, but not here because we can't do everything in every piece of course that we have, right? Okay, so that's pretty much what I wanted to tell you on this. But there are many other ways that you can approximate, obviously, complex and high-dimensional problems like Fourier series, for example, or even polynomials. You can use polynomial response surfaces or kernel methods or Gaussian processes, which normally Patrizio should talk about. You can use local linear models and domain-based proper orthogonal decomposition, which is what I talked to you about earlier. And yeah, and that's it. So that is effectively what you can do. Now, I give also in the notes some worked examples on how to use pins, physical informed neural networks. This is just comes later in this chapter 22, around page 210 or so, where we just derive everything completely by hand and normally in detail. I mean, it may not be perfect, but at least it's trying to explain also what pins are, how they work, and so on. And what will come next, which have not been able to deal with yet, will be the actual data only sort of methods. All right. So now what I'm going to do is I'm going to switch now to a presentation mode so that such that I can show you a little bit how this question of multi-scale comes up. And I just need a few minutes to open the right file and connect with the other computer. And I hope that this is going to work because you never know. In the meantime, if there is any question, maybe that is maybe the time to ask them. All right. Okay, so I have that multi-scale here. That's good. And now here I have the monkey. So now how do I share that screen here? Let's see if it works. I'm going to share PowerPoint. Yep, no problem. So question is, what is now being recorded? Ah, exactly. Okay. Now, can you confirm you see the screen just to make sure?
Yes, we can see your screen.
You see the screen. Okay, good. Thank you. Post sharing. What is that post sharing? Ah, that is here. Okay, so it is still recording. Good. Okay, so if you can see the screen, then let's start on that. So that's an illustration of what is going on in a real case scenario. That's extracted from one of our projects, which is called Panther Ray, which is funded by the European Commission under a grant of European Innovation Council. This is a collaboration with TU Delft in the Netherlands, with Politecnico di Milano, and with Derby University and a few companies that are manufacturing different 3D printed structures. So the goal of this EIC project is to come up with new materials that are recyclable and that are 3D printable, such that you can make recyclable objects, such as facades of buildings, such as screens that are used in office spaces, or benches that are made of wood, and so on. And the novelty of the project is that we will have humans in the loop, so the user will be in the loop, which you can see here on the screen. You will have the user taking ownership and trying to give feedback as to how they like the results, so that we can iteratively upgrade this, and we will use large language models in order to make that possible in a way which is systematic and rational and quantitative. So now, if you look at such a structure, you can see that we are talking about an optimization loop. So someone will at some point see a structure and they will say, okay, I like this surface effect here, but I don't like this other effect, and I like this effect, but I don't like that effect. Okay, so the problem is that there are very, very cool ideas in this project, which include, for example, using biomimetic structures such as those, which are copying the human body in order to come up with materials that are both light and durable. And if you look at the whole problem, you in fact realize that you have lignin and cellulose and all sorts of little crystals that make up the microstructure of this material, which then itself makes up a mesoscale model, and which itself is built into a macro scale model. So if you start from the macro scale model, that thing can look like a bench. So this is, for example, something you might want to build with this new 3D printing idea that is being developed by the partners of the project. And if you look at that bench, well, it looks like a bench, but it is comprised of a mesostructure. And that mesostructure is comprised itself of a microstructure. So that microstructure, which you can see here in the synchrotron imaging that was made by Politecnico di Milano in Grenoble, in France, you can see that you have a bunch of fibers everywhere. So if you zoom in here, you see a lot of fibers. If you want to count these fibers, you can't do it. It's a huge number of calculations. And finally, if you go into there, as I was saying, you see these fibers, and these fibers are not random fibers. They are made of lignin and cellulose and other sort of crystals. And you can look at them as molecular assemblies of structures, molecular structures. And well, of course, everything in there has an impact, but you need to decide what's really important. Do you need to take into account the molecular interactions? If yes, when and how? That's the question. And it's even more problematic that we are dealing with a structural optimization problem and also a shape optimization, topology optimization. And this is what we see here. In that region, we may have a different mesostructure, a different microstructure, different fiber alignments, and different molecular arrangements. Which means that even if we understand what's going on here, it may be that in this other area, which is structurally different, or in the vertical column here, will have different behavior. So that is super annoying because on top of that, we are dealing with an optimization problem. It's not just the fact of creating one bench and being happy with it. We're going to have to compute that for several types of structures. So we are really dealing with a combinatorially complex issue of having to solve a quite huge computational structural mechanics problem for various geometries under various loadings and various parameters. So that's the situation. And that's, in fact, why I called my team legato, because legato means that it's connected, so connected, linked. This is what you use in music to say that notes are connected, as opposed to staccato. Staccato means that you separate all the notes and they sound like this as if they are not linked together and you speak robotically. That is what staccato means. And legato is linked. And at the macroscopic scale, everything looks like it's linked. Everything is connected. And from far away, you don't see the discontinuities or the little gaps between things and the jumps and the atoms and the molecules and the interfaces. All of that is not visible. But at the macroscopic scale, you do see that. So what we do is we effectively orchestrate the music of materials in a certain way. And if you look at a raw calculation size, this is just to motivate the complexity that we have to deal with if we are supposed to solve these actual issues, these actual problems. If you wanted to solve a full panel using molecular dynamics, so molecular dynamics, just so you are clear, is, and this is also in the notes, by the way, I have a chapter on molecular dynamics, but molecular dynamics means you take into account the interactions between these atoms that you see here. So between two atoms, you have a force displacement curve, let's say some sort of potential. Lennard-Jones, for example, is an experimental potential that you can use. And you can use that to compute forces. So the force derives from a potential. You assume that. This is an empirical model in that case. And then you assume that if you take one of the carbon atoms or hydrogen, whatever, and you pull it apart from another atom, you will need to exert a certain force. And to do that, you can then compute all the sum of the forces on all the particles. And you can compute the dynamics of the system. That's why it's called molecular dynamics. So you take into account individual forces on individual atoms in order to compute what they are doing. So that's very discrete. And if the largest molecular dynamics runs are around 10 to the power 8 to 11 atoms, right? So these are really the largest. They are not run very regularly. Really, that's the largest thing. And if we wanted to take a very simple panel, we would need to have something like 10 to the power 16 more unknowns, right? So forget it. It's almost the Avogadro number. So just forget that. It's not going to work. So what is the next way that you can simulate? Remember, we're talking about a piece of wood that has fibers. These fibers can be modeled like that. They can be modeled with a cylinder, and you can decide to mesh the 3D cylinder and allow it to deform in plane. So that section area could decrease. It can be elongated in the longitudinal direction. You can do all sorts of things that you are interested in. So, interesting. I can use a laser pointer. Maybe I do that. Right. I have to leave for a meeting. Okay. No problem. I'll send you the recording. So you can imagine that you elongate in that direction. You can imagine that these things here will get smaller, so the surface area will decrease. Maybe here it will stay pretty much like that, and so on and so forth, right? So then you will have the deformed shape that could look like that. Okay, so that's typical what you can see. And then if you do that, well, look at the number of degrees of freedom. You have 10 to the power 11 degrees of freedom. So that's really large, really extremely large. It's, let's say, 2 orders of magnitude more than what is some of the biggest simulations. So let's say that is impossible. So we cannot take these things into account explicitly. Now, the other way is we say, and this is a very good modeling questions, how do I model the beam? Well, the beam I can model, as I said before, using a cylinder, but I can also use an actual beam. And the actual beam now can bend. That means that not only each point can displace in the three directions, as we talked about before, but now we can also have a rotation around one axis, a rotation around the second axis, and a rotation around the third axis. So instead of having only U1, U2, U3, you have now W1, W2, and W3. So you have now 6 unknowns per node. And you need a lot fewer nodes because each node is now richer. It can also bend. It can not only displace. So that means that to represent a cylinder, you can now represent that using only this little beam, which is a one-dimensional problem, right? I mean, one-dimensional representation. It can then bend. It can bend in whichever way we want, and it will have different nodes that are along the midline of the beam, and that will allow us to continue having deformation with much fewer degrees of freedom. All right, so that's good. This is cheaper, 50 times cheaper, but it's still very expensive. 8 to the power 10 power 9. This is really, yeah, in the order of weeks to months of calculations. So we don't want that. So what can we do? So instead, we can say, all right, so we are not going to compute all these things. We're going to compute simple representative volume elements. So in the notes, I define that clearly. What that means is that it is a size. So you can imagine that in the domain, you have inclusions. You can have, maybe fractures. You can have other inclusions that are larger or smaller or whatever, right? And that is the case everywhere in the domain. So let's imagine that you wanted to have a way to represent the domain, but without taking all of those inclusions and cracks and interfaces explicitly into account. What we could say is, okay, I'm going to draw a little window around, and I'm going to use that. But here, clearly that wouldn't work, because in that little window I just drew, you have only one of those inclusions. And clearly you have more than one. And you have none of these cracks that you have here. You have no interface, you have nothing, right? So that's too small. You can also enlarge it and maybe take that into account. Okay, well, in that case, statistically, you will miss something because you do not have these nice little interfaces or cracks that are initiating. So such an RV here has, let's say, a proper size because it's neither too small, meaning it does not include enough statistically relevant features, but it's also not too big because if you include all of that, well, then you include everything, yes, but you're very expensive because you have much more unknowns to take into account. So when you select a representative volume element, meaning something that represents the microstructure or whatever you're modeling, think that what you are representing here is something that needs to be representative, so meaning large enough that it includes enough of the statistical meaning, but also something which is sufficiently small that it doesn't take ages to compute. Okay, so that's what you'd need. And if you do that, then you can use whatever method. At the end of the day, just give me 1 second. Sorry about that. Okay, so now we have the RV. Okay, so if we do that, we see that if we want to do parameter sweeps, meaning now, you know, what would be a typical problem? Okay, here you have a stiffness for that particular inclusion. So I have to write with the trackpad, so it's really horrendous. Now you have E1, and I need to find a way to do that with the iPad, but I think I can't do it, is any. Doesn't matter. Okay, and maybe that other RV here is E2, but you don't know exactly what E1, E2, and so on are, because okay, they are, as we said before, parameters, and we measured them in the warehouse, and we did all of that, and we don't know what the temperature was. We don't know anything. So all these parameters have statistical distributions, but we're not exactly sure what they mean. And we don't know exactly what the value is. We don't know the mean. We don't know the standard deviation very precisely. So, we need to do some parameter sweeps in order to make that clear. And so we need to sample the distribution, use Monte Carlo analysis. So that means that you need not only to solve one RVE, but many RVEs, let's say 100 to thousands. And it's super expensive because then you need to also optimize. You can imagine that this is not only this, but also that's the shape of the bench, which looks really like a marshmallow. And then the shape of the bench, you have the RVEs everywhere in this thing, right? So it means that it may be also in some regions you have different properties, so you don't have the same RVEs. So you can imagine here you're now applying some loads. These loads are also parametric. So how in the world are you going to perform this optimization of the shape? Because even the shape, you don't know. You don't know that this is the best shape. Maybe you should cut the head off like this, for example, and this would be better. And, just get rid of that part. So that means that you have huge numbers of parameters in the optimization. You cannot afford to do that. All right, so then what do you do? It sounds like I know where I'm going. Well, yes, because we have, fortunately, the surrogate model, reduced order model. You see, this is not only a few equations on paper, this is also used in actual projects. And for the parameters, if we have about 10 to the power 3 parameters at the panel scale, we can be interactive. So that's the goal, to come up with those models. I mean, for now, we have not come up with those models, but Jakub Lenkiewicz and soon Patrizio will be working on this. And so we hope to be able to find some at least reasonable way forward. Okay, so that's just to motivate why we need surrogate models. And now I'm going to introduce to you in a different way what we talked about just now about the POD. So what is this POD? We are trying, in that case, let's say, to separate space and time. So we have one function u, which is a function of space and time, and we have two spatial functions, c of x, and two time functions, alpha 1, alpha 2. And what we do is we want to write the solution as a combination of c1 of x and c2 of x with coefficients, parameters, values that are alpha 1 and alpha 2 of t. So that's it. Now you can think of that in a more general way, that you want to do some sort of separation of variables. So you want to have a function of x I and a function of yi. That's it. And now let's see how that can be related to what you do in image analysis, because that is a very easy to understand problem that's going to allow us to understand two things. It's going to allow us to understand what we do with the reduction, so the POD. It's also going to help us to understand what is the limitations in terms of multi-scale, localization, nonlinearities, manifolds, and domain decomposition, and all that. So what we try to do is we try to look for a simplification of this image. We try to compress that image. So you see, this is a high resolution image. What is an image? It is a mapping from each of these little voxels. You perform a map from each voxel to a gray level, and the gray level is between 0 and 1. So that's the gray level. And you can say at that point X in this image, I have a gray level of, let's say, 1/4. And that gives you an idea of the color, of the darkness of that particular thing. Okay, so that's about it. Now, how does that work? Well, you're trying to perform a sum of two functions where you have separated the x dependence from the y dependence, because x and y are independent variables. So you can say, okay, I'm going to look at the x direction in that way and the y direction in the other way. And let's see now if I can find these coefficients, cx and cy, such that it minimizes the difference between my approximation, so that is the approximation, and the true solution, which is the true image, which is that guy here. And you want that true minus that in a certain norm be minimized. That's the idea. So how do you do it in a practical way? Well, you will start by having one mode. So you have a single mode now, and you're going to try to see if you can represent the image using only one mode. So you remember that is akin to what we said earlier about the POD modes. That would be phi1 related to the space VR, and now R is equal to 1. Here I called it NC. This is the number of modes. So what do we get if we get one mode? Well, we compress the image, but we really compress it a lot. And you can see that certain features that we would like to have, so for example, that nose, which looks pretty much like a hammer, that nose you cannot get here because all the lines are vertical and you do not see the delineation of that nose. You see mainly vertical lines. You see a few horizontal lines, but you see mainly vertical lines. Now, this is only what you see. You cannot see anything else. Now, if you add a second mode, the second function now enables you to see a lot more. Why? Because you have now here the possibility to see the intersection between this rectangle and the previous rectangle, which gets you closer to having a representation looking like the nose of this monkey. So NC equals 1, NC equals 2. You have only rectangles, and NC equals 3, equals 5, sorry, you start to see things, you know, looking banana shape, because clearly that now includes some sort of curvature, which you couldn't see with only two modes. You can see it here. The curves start to be visible. And now if you start to take NC equals 10, you start to see smaller scale features. So if you compare to the previous one, here you see this. On the next level, you start to see this guy here, which starts to be more visible. You start to see here, you know, the distance between these artifacts are visible. You know, these things, these features are now visible, which were not before. You see here the thickness of that is visible, which was not before. So smaller scale features become visible, and now you see now new features become visible, like those lines that were not visible before because you have a higher frequency. Simply, if you have a very coarse frequency, you're going to be able to see this. And if you have higher frequency, you're going to be able to see this. And so higher order modes allow you to see a peak in black, another valley, so it's white, peak, black, white, black, white, and so on, which allows you to see things like the nostrils and so on. And I'm sure that you're going to guess what I'm going to tell you next because it's starting to become obvious. This is the actual representation on the right, and on the left, you have the compressed image with 20 modes. So what is evident? Well, here on this image, you can see very clearly these little whiskers. And here you can basically see it, right? But it's not super clear. And these are the things that get clear at the last iterations. They are not clear for very low order approximations because, you know, these things are very small. So you need a very high frequency approximation, which means that R should go high so that the phi 1, phi R is able to represent, you know, this VR that we've talked about before is able to represent anything that's got to do with what you're seeing. You see here you have also small features in the eye, which you don't see at all in the other picture, simply because it is too narrow, and the frequency that you see here is far too large, too small, sorry. The wavelength is too large, right? So the problem here is really that you don't see anything related to these whiskers, for example. And the whiskers are a typical example that we covered in my team with Pierre Kerfreden again, who is now in École des Mines de Paris. And I highly recommend that you read his papers because he's extremely didactic and he writes extremely well. So if you want to know more about that, you can see that everything converges pretty slowly where you have things like needles or whiskers or whatever. So that means that this is really not working very well. All right, and what we will do in this particular project is we are going to be able to, well, solve this using all sorts of methods that I introduced also last time. And we hope to be able to take into account the user perspective using the methods that I introduced also last time, where I talked about categorical features using large language models and how we can include them in the search space, which is, you know, exactly what we had with this x1, x2 that I was telling you about earlier. Now we have x1, x2 and xn and x whatever, and all these latent variables, which you now understand what they mean. And yeah, and that's it. So at the end of the day, we should hopefully in this wonderful EIC project be able to do this. And because do you want to keep your no? Okay, so now I'm going to before we go further show you a final thing because I think it's quite interesting. Yep. So I'm going to go very quickly because I think we have, I don't know how much time we have, but it doesn't matter. I'll stop at 11:30 anyway, because then I have another meeting and then another class of 3 hours. Okay, now I need to share something different. I hope I have time in the time we have. Come on. Ah, good. This is very well done, actually. So I can share this. Okay, can you see now multi-scale methods model auto reduction on the screen?
Yeah, we can.
You can? Okay, amazing. All right, so now normally Alt Command P should work. Doesn't. Good. Okay, well, maybe I will just, Okay, good. All right, so now in the 7 minutes that are left, and yeah, if you have questions, you can ask them later on Signal, because I will really have to stop at 11:30 so that you don't collapse of exhaustion, and that I can just turn myself around to prepare for the next meeting at 12. So on a European project. So what I'm talking about here is the link between what I just told you about multi-scale methods and model order reduction using algebraic methods. So first of all, just imagine that we are talking about problems that have multiple scales. So I think for now you already understand what that means. You have these things that live in the smaller scales. This is a typical example of any alloy, like aluminum, steel that is made next to you in the high furnaces of ArcelorMittal. If you zoom in, you see that you have these little grains. These grains are polyhedral grains, and they have shapes, and they have interfaces, and along these interfaces grow cracks. And this is what people are interested in the steel industry, for example, but also in the aerospace industry. How do you take into account these cracks? Because if you need to solve the full problem, you need to wait quite a long time. And what you would like to do is to actually go and take a cup of coffee, come back and have a solution. So at the moment, you have to do what is called homogenization. So I don't take into account all these little grains. I just said I have a partial differential equation with constant coefficients. You can read that in the notes. I try to make it very clear there. So how do you actually do it? Well, you replace the heterogeneous fine scale model by an equivalent smoother model at the scale where the predictions are required. Because if you look here, you will see that the properties do this. They go up and down and up and down and up and down, because you jump from one grain to another grain, a grain to another grain. It's staccato, it's not legato anymore. So what you'd like to have is to have a model that knows where the cracks are going to initiate. In that region, it's going to have these little grains that are taken into account explicitly, but everywhere else, it's going to have an homogeneous model, a partial differential equation that has average coefficients, that doesn't jump around left and right in the staccato mode, but is very legato. Okay, so that's what you want, right? And this is in the paper Akbari, Kerfreden, and Bordas in Philosophical Magazine that you can take a look at. So that's really what you want, to have an interface between a fine scale problem and a coarse scale problem. And you want both to exist concurrently. This is called a concurrent method. So you have a fine scale and a coarse scale that exist in the same place, and they interface with each other along a certain line. This is called the adaptive coarse-fine interface. And you need to do that in a smart way to conserve energy and to make sure that you have continuity of the areas that are, of the state variables that are important. So we did that with Timon Hatschuk, who is in Weimar, at Bauhaus Universität in Weimar, in Ostdeutschland, at least the previous version of Ostdeutschland, now, of course, reunified, but you know, in that area, it's a super nice place. If you want to visit him, he's a very nice person, and he's very knowledgeable about molecular dynamics, also continuum methods, and the coupling between these two. So you can have molecular dynamics here close to the crack tip, and far away you have a continuum model. So again, staccato here, legato elsewhere. Staccato here, legato around. And then you have this continuum transition from the continuum to the molecular dynamics. So that was called concurrent methods. You have both scales living in the same domain. Now you have another approach which is a bit different, where you have now a domain which is entirely comprised of a continuum PDE. Now the difference is that at each point of that continuum, so you have a continuum PDE with coefficients, but these coefficients are now not set in stone, you know, computed in that warehouse by 25 degrees and 1 atmosphere, but now they are computed using representative volume elements, which can evolve. So you can imagine that cracks are forming inside here, they are propagating, and they are growing, they are finally splitting the RVE, and at some point a crack is being initiated in the macroscopic scale. We have a few papers with Timon exactly on this, and that shows you how to introduce cracks at the macroscopic scale using whatever happens at the microscopic scales. And I think you can take that idea and transfer it to other fields where these discontinuities happen. Now, the thing is, at each point here, you're going to have to solve an actual problem, because you're going to compute in the macroscopic problem, the coarse scale on the left, this L shape, you're going to compute a strain field, apply it on the representative volume element I introduced, then get a stress field and some sort of tangent stiffness matrix that gives you an idea of how the material is behaving at that point in time. And then you're going to pass that back to the point, compute the out of equilibrium forces, assemble all this in the internal forces, and then compute again. So that's quite costly, as you can easily imagine. And the way it goes is like that. You load. So this is a stress vertical, strain horizontal. You load, you load, you load, you load. And at some point you reach a peak because the cracks have percolated. They have completely cut the representative volume element. And you have no tangent stiffness anymore because it's not positive definite. You lose ellipticity. So the PDE changes type, no uniqueness of the solution, loss of material stability, and you are done. When that happens, you need to replace the element where that happened by the actual microstructure, or at least one instance of that microstructure, because as you can imagine, this is statistically determined. It's very difficult to, of course, know which microstructure you will have. Practically, it's actually impossible. So you need to run Monte Carlo simulations on the different microstructures. So this is in the same paper, Philosophical Magazine. The cracks are initiating in the microstructure. It is here handled explicitly, and it's propagating. And you can see that it's 1,000 times fewer degrees of freedom than in 3D, which is pretty cool. And you can grow the crack in a way which is very logical and natural. Okay, so now what do you do about that? You have an adaptive multiscale where you lose material stability. You replace our representative volume element, which ceases to exist, by an actual representation of the microstructure with all the grains individually taken into account. Now, how do you, and I'm sorry, it's 11:30, but I need only 2 minutes. How do you now solve the problem using algebraic model order reduction methods? Well, in that case, you use pre-computations, so pre-computed solution snapshots to accelerate online simulations. And this is the idea of the method of separated representation, which I showed with the monkey. Again, I'm taking the example of the beam, now shown a bit differently. And now the beam is a little bit different from before. So you apply, as we said, a force FD1, and you get a solution snapshot S1. You apply FD2, solution snapshot S2, and so on until you applied an S. Now I called it S. My apologies for the lack of logic in the notations. And then you perform the singular value decomposition to obtain the most energetic modes. And what you get is mode 1, which looks like the first mode of deformation of a beam, very logical. Mode 2, which looks like the second mode, and mode 3, which looks like nothing really at the moment. Okay, so you look at those 3 modes. And now let's imagine that because you're really unlucky, the load that needs to be computed online, because until now we were offline, all that is done offline, right? Before you need to compute the fast simulation, but now comes the load that you need to compute the fast deformation for. Let's say that your airplane is flying or your patient is on the table, you need to make a fast decision, but very bad luck, all the loads you had applied were below the elastic limit. And now someone gives you a load which is beyond the elastic limit, which means that all the modes you threw, you computed, you can throw in the garbage, because now you have a kink, because the beam is actually breaking. And if it's breaking, you have a jump in the first derivative here, and that jump cannot be taken into account by smooth functions. So again, we have exactly the same problem as what we said with the manifold problem, that we have a solution which is not easily interpolatable or easy to approximate using C1, C2, and C3, because these are smooth functions and they are low order. And here you would need a very high order mode in order to capture that kink. Similar problem with the Gibbs phenomenon. If you want to capture singularities or discontinuities using polynomial functions, it won't work. So here, same problem. You have a kink and you need to capture the kink. So what do you do? Well, the solution, unfortunately, is not in your snapshot. So you need to do something. And that's what you see in these ideas. What you do is you split the domain into subdomains, and there are certain domains which are far away from the crack, which you will be able to very easily reduce because they do not deform too much. But the one that is close to the crack, like for example, the one at the top left center of the beam, where theta equals 15, for example, well, this one you will need to actually compute explicitly. And why? Because if you have this theta equals 15 degrees angle, you see the crack propagates in this direction. If you change the angle of propagation to 45, you see the crack propagates in a completely different direction. So you have some sort of residual check here that will tell you whether you should or not assemble these residual, or if you should perform the reduction. And that's it. I'm done. Sorry, it took 4 minutes more instead of 2. Do you want to ask questions now, or do you want to ask them maybe online or in any other way later? I hope actually that was useful. I really did my best to be as clear as I could. I hope it made some sense and you could get some value from this lecture. But in any case, I'm not disappearing. I'm here.